Welcome back. We're still doing a revision on redox reactions. Now we are able to represent redox reaction, but in a given example, there are certain techniques also that we need to kind of master. So let's look at the next set of examples and see how best we apply what we've learned. Right. So the equation below represents a redox reaction. Immediately we're thinking there is transfer of electrons, there is loss as well as gain between two substances that are reacting. So in this redox reaction, there is 8 grams, that's the mass of iron 3 oxide. The formula is given. The iron 3 oxide reacts with 3.8 grams of aluminium. Right, so the balanced equation of reaction is already given to us. So this is the equation that we shall focus our attention on. Right, now the first question says, assign oxidation numbers to all the elements in this reaction. Now immediately we recognize that this question is about us going back and reminding ourselves of what is exactly important in as far as the rules that we pay attention to when we assign oxidation numbers. There's a whole set of rules that we need to remember and know when to apply each one of them in given scenarios. So in this case, we are going to assign, let's start with iron 3 oxide. Now, which rule applies in this case? We know that oxygen in its combined form, the unit oxidation number is -2, right? So here oxygen is -2, right? But the total is -6 for oxygen, right? And then for iron in this case, because of that chemical formula, is +3, right? It's +3, the total is +6, which gives us a total of 0 for that. Okay. Now, if we focus our attention on aluminium, in its purest form, any pure substance as an element, it has an oxidation number of 0, right? Let's look at aluminium oxide. We apply the same rule in aluminium oxide, 3 oxide, as in iron 3, right? In oxygen, in its combined form, it's -2, right? Now, the unit oxidation number of oxygen is -2. Then for oxygen, the total is -6, right? So in this case, iron is +3, all right? Meaning the total, because there's 2 atoms of aluminium, is +6. So if you say +6 minus 6, it gives us a total of 0 for this compound. And then iron as a pure substance, which is an element, then it has an oxidation number of 0. So these are the different rules that we definitely want to apply in as far as oxidation numbers. Now immediately one thinks, why is this important? Why are these rules important? For us to keep track of changes in oxidation number of a particular substance in a reaction, we are able to understand whether that substance undergoes loss or gain of electrons in as far as the transfer in the context of redox reactions. Right. Okay. Now the follow-up question says, write down the oxidation half reaction. So oxidation involves loss of electrons. So we know that iron here is +3, oxygen is -2 in its combined form. This one is 0, +3, -2, that is 0. So when oxidation takes place, the substance actually loses electrons and there is an increase in the oxidation number. So if you look at, for argument's sake, aluminium. Aluminium initially, it has an oxidation number of 0 and then it changes to +3. What has happened to aluminium? Aluminium has lost electrons. And then how do we represent this half reaction? It's going to be aluminium, okay, metal, to give us aluminium, okay, 3 plus 3 electrons, right? So this is the substance that loses, okay? So what this substance has undergone is oxidation, which is the loss of electrons. And immediately we're thinking in terms of language, this substance is actually our reducing agent. So in other words, we are saying aluminium is a stronger reducing agent, okay? Because what aluminium has done here, it has displaced ion in the oxide, okay? So we're saying aluminum is a stronger reducing agent. So that's straightforward, right? Okay, and then write down the reduction half reaction. So in the background of aluminum displacing iron, okay, we are saying that what happens to iron then actually gains electrons in the process. And the process of gaining electrons can be represented in the form of a reduction half reaction. Exactly how do we do that? Right, we are saying that if we look at iron, here iron is +3, okay? On the other end, it's 0. So what has happened to the oxidation number of iron? It has decreased, right? Or it has become less positive, if you want to think of it that way. So how do we represent that in terms of the half reaction? We are saying that iron 3, okay, plus 3 electrons, okay, it gives us iron. All right? So what has happened to the iron 3? The iron 3 ion is the one that undergoes reduction or the gain of electrons. So what name do we give to the substance that undergoes reduction? We call it an oxidizing agent. Okay, something of particular interest to us now is to understand that to say iron undergoes reduction, it's not entirely true. Actually, it's the iron 3 plus ion that gains the electron. So to say ion, you are referring to the atom of iron, which is a misrepresentation of what exactly is happening. So pay careful attention to the actual species. The question may ask in terms of the formula or the name, or it could be both, formula and name. You need to pay careful attention to those keywords, right? Okay, so this is the reduction half reaction, okay? So in the above redox reaction, identify the oxidizing agent and the reducing agent. So we have done that. We said the aluminium undergoes the loss of electrons. Okay, so if we say aluminium is a reducing agent, we are saying aluminium undergoes oxidation. So it's the aluminium atoms or metal aluminium that undergoes oxidation, right? And then an oxidizing agent undergoes reduction. So what is reduced is actually the iron 3 plus ions. So be careful of that. So these are the formulae of the reducing agent and the oxidizing agent. So aluminium is the reducing agent because it loses. Iron 3 ions is the oxidizing agent because it gains electrons. So that's very, very important as well. Now, stoichiometry is, one part of chemistry that is very, very broad, and it's very important for us to emphasize that it can be anywhere where there is a reaction. We can talk about stoichiometry in terms of, the mole concept. Understand the importance of the mole as the SI unit of quantity of matter. So everything is about the mole, because a mole of any substance contains the same number of particles. So as a way of measuring quantity of matter in a chemical change, we talk about the mole. Okay, so as long as there is a reaction, we can allude or talk about the stoichiometry involved in that chemical change. So in this example, we've got 8 grams of iron 3 oxide as well as 3.8 grams of aluminium. So the reaction runs to completion. What does that mean? It says that this reaction occurs to a point where it stops. Whether the aluminium was used up or the iron 3 was used up, it doesn't matter. But one of the two reactants reacted completely. So the question demands that we determine the percentage yield given the mass of iron that was formed. Right. So first things first, the equation of reaction is balanced for us. So the stoichiometric ratio in which these react is that 1 mole of iron 3 oxide reacts with 2 moles of aluminium to give us a mole of aluminium oxide and a mole of iron. So the stoichiometric ratio, in short, is 1:2:1:1. Right. Now let's ask ourselves, in 3.8 grams of aluminium, how many moles are present? So number of moles of aluminium, okay, is equals to mass of sample of aluminium over molar mass of aluminium. So what do we have there? It's going to be 3.8 grams, okay, divided by the atomic mass of aluminium is 27, right? Okay, in this question, it says here, the equation below represents a redox reaction that has a lot to do with the transfer of electrons. There is 8 grams of iron 3 oxide that reacts with 3.8 grams of aluminium according to the balanced equation of reaction. So this reaction runs to completion. It means one of the two reactants actually gets used up, and then the reaction stops for that reason. So we want to determine the percentage yield given that 4.76 grams of iron was formed, right? So what is important here is to understand that the stoichiometric ratio in which these substances react from the balanced equation is it's actually 1, okay? Just to correct that, right? It's actually 1 is to 2 is to 1 is to 2. So in terms of stoichiometry, this has to do with the mole concept in terms of the quantity of matter as an SI unit. So we ask ourselves, how many moles of aluminium are present in the 3.8 gram sample? So number of moles of aluminium is equals to mass of aluminium over molar mass. So the mass is 3.8 grams divided by the molar mass of aluminium, which is actually 27 grams per mole. So how many moles of aluminium do we have in this case? We can quickly go to our calculator, right? What do we have? We've got 3.8, right, divided by 27, right? So in this sample, there's actually 0.14 moles of aluminium. So 0.14 mole, right? Equally so, we want to ask ourselves, how many moles of iron 3 oxide are present in 8 grams? So we are saying moles of iron 3 oxide, right, present is equals to mass of the sample, which is 8 grams, divided by 160, which you get from the periodic table. So how many moles is that? So if we are to calculate that, we've got 8 divided by 160. Okay, this actually gives us 0.05 moles, right? So this is 0.05 moles, right? So if 1 reacts with 2, it says to us that the aluminium oxide is actually our limiting reagent. So all the 8 grams of aluminium will react, right? So 1 mole of aluminium oxide of iron oxide gives us 2 moles. So the number of moles of iron that will be formed is equals to mass over molar mass. So what is the mass that we are looking for? We're actually looking for the mass of iron. So if there is double the number, if 1 produces 2, so in other words, we'll have 0.05 times 2, which is 0.1 mole, okay, is equals to what mass will be produced. What is the molar mass of iron? It's 56, right? So what mass will be produced in this case? We can go to our calculator and say 0.1 multiplied by 56, which is the molar mass. This gives us 5.6. So 5.6 grams theoretically must be produced, right? But we are told instead that 4.76 grams of iron was produced. So percentage purity, okay, is equals to, actual yield, okay, divided by theoretical, okay. We multiply this by 100, okay. So the actual one that was obtained is 4.76. 4.76 divided by the theoretical, which is expected, which is 5.6. We multiply this by 100, we'll get the percentage purity. So if we go to our calculator, okay, what do we have? We've got 4.76, which is what was actually formed, divided by what we expected from the stoichiometric ratio, which is the theoretical, which is 5.6. Okay, then we multiply that by 100. This would going to give us the percentage purity. So our percentage purity in this case, actually that's 5,6. If we can quickly go back and correct that. So that's 5,6, right? Okay, this gives us 85% purity, right? So this is 85% purity. It means then in this sample of iron, it means that 15% of this sample contains impurities, right? So the long and short of it is that as far as the stoichiometric problems are concerned, let's pay attention to the fact that if the equation is balanced, what does that tell us? It tells us the stoichiometric ratio in which these substances actually react with each other, right? And then the whole stoichiometry comes in because this is a chemical change or a chemical reaction wherein new substances are formed. And the mole concept, how does it fit into this? We understand that the mole is actually the SI unit of the quantity of matter. So we don't talk grams, kilograms, tons when we talk amount of matter in a chemical reaction, but we talk of the moles, which is why we always go back to the formula, number of moles is equals to mass over molar mass. So this is just one of the examples to say that stoichiometry, as long as there is a chemical change or a chemical reaction, it will always be featured, right? So if we are to kind of analyze the whole idea of this problem, we are saying that if the stoichiometric ratio is 1:2, it means a mole of iron 2 oxide produces double the number of moles, which enables us to get the mass of iron theoretically that we are actually expected. So this is what is expected, okay? This is what is expected, right? But in reality, this was formed. So this is the actual yield. This is the actual yield, right? So these are some of the, the ideas that must obviously come to mind, right? For now, we'll take a short break and look at more examples after the break. See you shortly.